All right, now let's talk about some more specific types of random sampling. Sometimes it is not effective to completely leave the sampling method up to chance due to the presence of certain variables. Oftentimes, we need to reduce the variability due to chance by performing some specialized types of random sampling methods. Now, the first one also looks like SRS, but this one's just referred to as the stratified random sample. We divide the population into subgroups that are homogeneous, often called strata. Within each strata, we then select an SRS, and the selected units are combined to form the sample. So, homogeneous meaning that they are similar in some characteristics. So some examples are grade levels, the difference between juniors, seniors, sophomores, freshmen, middle school versus high school, etc. Gender identity, such as male, female, non-binary. Health status, whether someone is active, non-active, any underlying health conditions. Age, are they a millennial, Gen X, Gen Z, Gen Alpha, etc. But we're essentially we're grouping them into these similar characteristics called strata. And a way to remember this is sum of all. So I would break them into different groups. Of course, there can be more than 4. But basically, if I break it into 10 groups and I want to form a sample of 100, well, 100 divided by 10 would mean I'd need to sample 10 from each group so that they're all consistent. Now, that could be the other way. Maybe you have this weird 50, 25, 25 split. Then you'd need to select 50% of one group and 25% of the other groups, etc. But you're basically just keeping your strata as similar to the population as possible. So that will depend on just what information you have. Now, sometimes it's a little too difficult and too time consuming to form the strata and find these characteristics. So you do something that's called a cluster sample. And here we divide the population into smaller groups called clusters, and within each group there is heterogeneity. However, we assume that the clusters are similar to one another in their composition. An SRS of clusters is selected from the population to form the sample, and once we have those clusters, data is collected from all observations within those selected clusters. So you can actually select multiple clusters or just one cluster. And typically this one's done by location, meaning like something geographic, like I'm only going to sample the eastern states or the western states. Maybe this is like neighborhoods and neighbors. I'm only going to sample Fulshire and Humble. Or maybe this is proximity. Maybe I'm going to sample the Heights, but then I'll sample like I-10, downtown, Allen Parkway area, etc. So it's usually based on some type of like location into where you're sampling. And so where strata was sum of all, this is now all of sum. So you form these clusters, you assume everyone is pretty, not the same, but you assume there's enough differences in the different neighborhoods of Houston that it's okay if you sample Friendswood versus if you sample Humble or Fulshire. And I'm sorry I keep referring to those examples, that's just where I've spent my time this summer. So all of sum here is for clusters. So we have stratified, we have clusters, and now the other type is a systematic type of sample. Here we pick a random starting point, which we call H, and within the population, and here we obtain the sample by selecting individuals from points using a fixed periodic interval. We select every kth person. So here, if I assume I'm starting at the first person, and then I'm going to select every third person, notice I'd pick person 1, person 4, person 7, person 10, a little random sampling thing at the airport or like when you're waiting in line for a contest and they'll randomly talk to people throughout the line, things like that. So there could be a predetermined starting point and a predetermined interval. Now caution with this because we said previously that if it's a true simple random sample or some random sample of that nature, then there should be equal chance for everyone to be represented in the sample. But you'll notice here that if you're not every third person from that starting point, you basically have no chance of being selected in that sample. So we're not entirely sure if this is a true random sampling method, but it is a different approach to it. So again, we have the strata, they're all the same. Cluster, there's enough differences. So this is differences between, this is differences within, and then this is just, whoa Nelly, go for it. So let's go ahead and look at these 4 examples here to talk about the sampling methods that we've just addressed. So again, SRS, stratified, cluster, or systematic. So I'm going to give you a few moments here. Go ahead and pause the video and try out identifying the sampling method. Okay, so hopefully not too complicated. And I went ahead and highlighted some key language in each of the problem statements so that you can get familiar with the idea of these types of sampling methods. So in the first situation, to conduct a pre-election opinion poll on a proposed amendment to the state constitution, a random sample of 10 telephone prefixes, the first 3 digits of the phone number were selected, and all of the households in those prefixes were called. So I am here, my clusters are going to be those prefixes. So if they contain 281, 713, 832, any number that has that prefix is going to be sampled. All of the numbers with that prefix are sampled. This would be an example of a cluster. Now, to maintain quality control in a brewery, every 20th bottle of root beer coming off the production line was opened and tested. We've got a starting point, we've got this interval. I'm selecting every 20th. There's not really too much going on here. This is just a random systematic sample. Next up, subscribers to a magazine, Sound Alive, were assigned numbers. Then a sample of 30 subscribers was selected by using a random number table. And the subscribers in the sample were invited to rate new headphones for a What Do Subscribers Think column. So here, this random digit table, everyone we obtained, assigned, select, yada yada. Usually when you see the hat method, random number generator, or random digit table, this is going to be indicative of a simple random sample. And then lastly, to judge the appeal of a proposed television sitcom, a random sample of 10 people from each of the 3 different age categories was selected, and those chosen were asked to rate a pilot show. Here we could assume that since there's 3 different age categories, everyone within those age categories is going to be relatively the same. This would be indicative of strata. So this would be a stratified random sample. And I just put strata there. My bad. Typo. But, so those are just the 4 basic types of random sampling methods we can use. Now, let's have a quick discussion here, because we mentioned that we use random sampling to address particular variables. So let's take a look at what that could look like. Suppose we want to estimate the mean amount of a certain crop compared to its distance from a river. The field is square and divided into 16 equal-sized plots, and a researcher only has the resources to sample 4 plots. So here are my 16 plots. We can see here's the river, and this is indicating the yield from the plot. So plot 1 yields 4 units. Plot 2 yields 29. Plot 3, 94. Plot 4, 150, etc. So I can only sample 4 plots. I want to sample the, what should I do? Should I sample all the ones next to the river? All the ones furthest from the river? Should I randomly select every 4th one, every 3rd one, etc.? Well, if I can only sample 4, I want to be very strategic. I would probably want to sample some of all of the different distances from the river. So sum of all would probably, a good situation here would be a stratified random sample. And here we'd stratify based on distance from the river. And so, plot twist, a stratified random sample, although it's the most time consuming, is usually our most representative type of sample because we are keeping our sample proportional to the population. We're trying to ensure that it's as similar as possible. Whereas using a cluster, systematic, or simple random sample might have a lot of variability or pick up some unknown pattern that we weren't aware of. And now let's take a look at this question. What could those unknown patterns mean? Well, why is proximity to the river something we should consider? Well, let's look at these 4 plots right here. And I'll go with green since we're talking yield. So let's look at plot 4, 8, 12, and 16. When I look at the mean amounts, notice that these are generally the largest mean amounts of yield in this entire field here. Meaning that the closer to the river they are, usually there's going to be more yield, and that's just because access to water, maybe the sun hits better there, maybe the soil's more fertile because of the water. So this is something we should consider because if we did a cluster sample and we just clustered the entire 4 plots next to the river, we might say, yes, let's go plot the crops right here. But then we end up selling the plots 1, 5, 9, 13, and where there's really low yields. And now someone's going to get really mad at us because we just said, hey, well, there's all of this yield here to be had. We're saying here's this promise, and then we're failing to deliver. So the proximity to the river is a special type of variable that we call a confounding variable. And a confounding variable is a variable that is closely related to the explanatory variable and has some influence on the response variable and may cause a false association between the two. And there's a sentence stem there. But basically, we have this picture going on. I'm trying to show that there's some relationship between X and Y, whether it's cause and effect or some type of association. But here I have this unknown variable, that is kind of related to X, but then also has some influence on Y. So I can see now with this weird triangle, I can't tell if X or Z is causing this change in Y. So they both have an influence on the response, but I can't distinguish which variable is causing that. So in summary, we've got the following. Our population, again, here's me, the researcher, here's our population. I'm looking at this characteristic. An SRS, I'm just going to randomly select a few people to form a sample from this population. In a systematic sample, I'm going to pick every third person, and I randomly pick here the second person. So my starting point is 2, and then I'm going to select every third person from 2. So 2, 5, 8, 11, etc. Now, if I want to be more representative and more accurate with my data collection here, I'd use a stratified sample where I actually break the population into these strata, some homogeneous characteristic, and you can see the groups here are pretty similar, and from there I'd assign a certain amount from each characteristic to form my sample so that it's representative of the population. And then lastly, we have the cluster sample. This is our heterogeneous, and we assume that they're similar in composition. So here you can see I have clusters of 3, but here, right, this will be an entire cluster of just this characteristic. Whereas in the other clusters, you see there's some variety between the orange and the gray. So in a cluster, I'm hoping that there's enough heterogeneity in their compositions, and I'm just going to sample everyone within those clusters, hoping that it's enough. But again, the issues with SRS, systematic, and cluster is that there might be some high variability, or there might be some unknown pattern that we pick up, whereas in a stratified, we're typically more representative. And then the next thing is this idea of confounding variables. Our explanatory variable, the independent variable, the who, we're trying to show that relationship with the response variable or the dependent variable, but here's this unknown confounding variable that has some relationship with the explanatory and has some influence on the response. So here's 2 examples here. High ice cream consumption and the number of sunburns and hot temperatures. Well, hot temperatures could cause more ice cream consumption. Hot temperatures could cause a higher number of sunburns, but that doesn't necessarily mean that consuming more ice cream causes more sunburns, right? There's this unknown association that exists there. Or perhaps we're looking on the effects of alcohol use on lung cancer, but maybe people who identify as alcoholics are also chain smokers. And so now I'm not sure which one has a greater influence on the lung cancer. Is it the alcohol use or is it the smoking? Well, I'm not quite sure because there might be a giant overlap between these 2 groups. So those are the ideas there. There's types of sampling methods, and we use, it depends on the situation on which one we want to use to address the confounding variable. And remember, we want to be low bias. We can't ever truly eliminate bias, things like that. So I almost said next episode because it's so much fun talking about stats. But in the next lesson, we're going to talk more about bias and what this looks like in this course. So stay tuned.